Hello friends, I'm going to talk to you about the concept of load path. The concept of load path is one of the most important concepts for mechanical and structural designers and also stress analysts. However, this concept is not known to many people as it is not taught in the colleges. I learned this concept through my own experience in the industry. This concept helps to avoid a lot of trial and error later on in the design process. Consider a step bar as shown in figure 1. It has uniform thickness and it also has a fillet at the region of transition of the width from one width to another. We fixed one end and we apply the tensile load of 1000 newtons at the other end. So we get a free body diagram as shown in the figure. So there is 1000 newtons of applied force and 1000 newtons of reaction force acting in opposite directions. Now I'll be showing you how to draw the load. To do this, you have to connect the reaction force lines to the applied force lines through a spline. And as you can see on the screen, the red dotted lines represent the load path. And you can also notice that a part of the structure is outside the envelope of these red lines. And that is the path not covered by this load path. So in those regions, it is favorable to place the unavoidable holes, slots, bosses, etc. So that will result in minimal increase of stress. And what is the significance of the load path? Now, if you see the engineering structures, we need to accommodate various stresses like holes, bosses, slots, etc. However, often we have a choice about where we can locate them. So, in order to decide where we can place the stress raises, this concept of load path is important. Now I'm going to show you through FEM analysis how placing a hole within the load path and how placing a hole outside the load path affects the stress distribution differently. First, we run the analysis without any hole in the original structure. Let us have a look at the results. So you can see the results on the screen. The maximum stress is coming somewhere around 9.5 megapascals and it is at the fillet at the transition region. And if you look at the green region where I'm going to place the hole, it is somewhere around 4.5 megapascals. Now let us introduce a hole outside the load path as we had seen through the through those red lines, outside the envelope of those red lines. So as you can see from the results, the blue region where we have introduced the hole, it remains blue. The stress has not changed much. Now next we will see what happens when we place the hole inside the load path. Now in this figure I have placed the hole inside the load path and performed the FE analysis. You can see the results on the screen. As you can see, uh, the maximum stress has actually increased slightly, but more importantly, we want to see what is the maximum stress at the region where the hole has been introduced. So let's have a close-up look at it. Now, if you zoom into that region where we have placed the hole, so the same region which without the hole had a stress somewhere around 4.5 megapascals is now having a stress somewhere around 10 megapascals, as you can see from the close-up plot given in the inset. So this shows that when we place stress raisers within the load path, it can greatly increase the stress because of stress concentration. The same thing, if you place outside the load path, it has minimal effect. I conclude by saying that the determination of the load path helps us to decide the location of the stress raisers in such a way that we can maximize the strength of the structure. Thank you.